Hey guys, so this is a re-recording of Lecture 4 on the DH algorithm. I had to re-record it because, as you're aware, if you were at the lecture, the computer was not behaving. But I'm going to do a re-recording because this stuff is quite important for coursework 1, at least, and also your exam. And if you want to become a robotics engineer in general, this is probably one of the most, just said that right, one of the most important algorithms you can learn. So you're not going to hear yourself shouting out the answers like last time, but I'll explain the rules clearly and so forth. And again, if you have any questions, feel free to email me or Steve about the application of the algorithm. But there was a worksheet I released last week for you to try out, and I'm going to make a video a bit later today as well about how do I answer those and actually how do we apply the algorithm. So let's make a start. So first of all, the DH algorithm. So hopefully you remember from lecture 3, maybe you watched just a video just now when you're revising. When we did lecture 3, we did the homogeneous transformation matrix. And the problems we had with just the standard homogeneous transformation matrices, HTMs being, for instance, if you're doing rotations in terms of X, rotations in terms of Y, we're going to have those matrices. So, for example, we would have something like, got to remember off the top of my head now, cos minus sine, of course the angle, sine and cos, I won't write the whole thing. But the problem we had when we were applying these matrices to robots was we could technically assign any kind of axes to the robot. So for example, if I just do a very simple robot, so there's a rotary joint and then I've got a prismatic joint going this way, for example. I could assign my axes in any way I wanted. So, for example, I could assign Z to be in this direction. Hold sec. Yep. Go do Z. I could have my X then in this direction. And then I could have my Y in that direction. Nothing wrong with that. When it came to the next part of the robot, I could just as easily say, now my Z is in... Well, I could say this is X. Z is coming out. And then Y is upwards. Always using the right-hand set, of course, to get these axes. But the problem is, I mean, yeah, sure. If I'm taking this as the base frame over here, this is the base frame, and I'm trying to find the position of the end effector, which I'll just draw over here, P, with respect to the base frame, y0, x0, and z0, 0, 0, 0, well, nothing wrong with that. Those transformation matrices will definitely place that P within the base frame. So when we're doing these transforms, we're basically trying to find where is the location of P with respect to the base frame. Nothing wrong with just doing some transformation matrices, doing some translations along one of the axes. It will get you the right answer. But what if one of your colleagues working on the robot too decides to assign the axes in a different way? They're not doing anything wrong either compared to what you're doing, but you've got completely different transforms for the same robot, and you're actually going to get kind of different results. Who's to say that, for instance, Z could be downwards? You could say Z0 is downwards, and therefore they're going to get a negative value for Z in their P, for example. So there becomes a problem in that we need a system whereby everyone can follow the same rules, we follow the same transformations, and that when we are designing our robots within a team of engineers, we know exactly where different angles are and what they describe and what a translation is in respect to the robot. So we need some bespoke tools in order for us to basically have a coherent method across the world. And this is where the DH algorithm comes in. So again, I'll do my writing again. So this is why we're doing the DH algorithm. So we saw issues with HTM in that I can rotate axes, and I probably should say different from the lecture notes. and place axes in any direction I want. Okay, so this is a problem when designing robots. Oops. In teams of engineers, since, well, especially in software, because obviously we've got to program all these turns and angles when we actually want to make these functional robots, especially in software. So the solution to doing this is the DH algorithm. So DH algorithm is the solution, and it basically, it's ever so slightly different to what we've done already. So it's a slightly different approach. My handwriting is just as terrible. Slightly different approach to what we've done. It produces an easier means of analysis lost where I am, where joints are offset, i.e. a SCARA robot, or more complex manipulators, So what I mean by that is, if I draw out a SCARA robot, we start off with a rotary joint, like so, and then how it's made up of is basically lots of right angle turns, where we got that, and then it's got another sort of joint here as well, where then there's a prismatic joint on the end. And when there's an offset, so the offset, i.e. being this bit here, where you got an angle turning and so forth, and a translation along another axis, it can, if you're just doing the HTM method, what you would have to do in order to be able to apply it is you need to have several more axes. Because the standard HTM method we described above here, it doesn't, well, you can, but usually a better process of doing it is adding a new axis over here. So you'll have your axes over here already. Then in order to go and find out the translation to the next frame, when you've got an offset like so, the method you have to do usually is to add a sort of sub frame over here, for example. And therefore, in doing that, you have to just make the calculations that little bit more complex. So for every time you've got a sort of offset joint or something like that, you need to add a few more frames just to get the correct translation. With the DH algorithm, this sort of right angle turn is already preset into the algorithm, as you might be aware from the lecture already. So that's why it does make it a bit easier. We don't have to make multiple frames. The DH algorithm allows us to just go from one frame to the next frame and accounts for any offsets already made in the robot. So I'll leave that there. Well, no, I'm not going to produce this, it's just for lectures. Get my pen back. There we go. And it also simplifies forward kinematic analysis. Partly from the reason above. But the problem is, so it's easy to assign and perform forward kinematics, but it's only easy once you've assigned the frames. Assigning the frames can be one of the challenges, especially for a more complex robot. So only once the frames have been assigned. Frames have been correctly assigned. Okay, so before we can actually apply the DH algorithm, we need to apply some rules, and there are 4-ish rules, although rule 2 has a few subsets to it. So, how do I add a new page? Oh, press this button. There we go. All right. So, the DH rules. So, rule number 1 is the z-axis is always in direction of the joint axis. So in this course, we're only going to deal with 2 joints. We're going to look at the prismatic joint and the revolute joint. Makes it a bit easier. So, for example, if we're looking at a prismatic joint, so that would be like so. That was not the best drawn. That'll do. If we've got a prismatic joint over here, we would assign our z-axis to be along this line. So where does the joint flow from? So where does the link flow from the joint, essentially? So we would assign our z-axis in this direction. Oops. If we've got a revolute joint, so do a little circle here. Position my drawing thing a bit in a better place. Wait, there we go. So if we've got a revolute joint, again, the way to think about it is where does the link flow from the joint? So in this case, obviously it's going this way. That's our Z, where a rotation is going around like this. Oops. That'll be our theta in our revolute joint there. Quite simple. So where the link flows from the joint, that's the direction of our Z-axis, and that's always going to be the case. That's the easy one to do. You can never really have a dispute with that one. Number 2, and this is the XK axis, is normal sorry, to both the current ZK axis and the previous ZK-1 axis. So I drew some drawings to make sense of that. So let's imagine, for example, the previous axis was going into the screen as we go now. So into the screen there, and that's going to be our ZK-1. And then our current axis is now going upwards. So that's our ZK. So if we now put them together and analyze the frames, we would see that we get, so move over here, we would have ZK up here and ZK-1 in that direction, creating a plane. We would therefore assign XK to be normal. So XK would be in that direction. Now, when we were in the lecture, there were some questions. One of the questions was, could, for example, XK be in this direction as well? Could it be going to the left? And the answer is yes, it can. It still follows the rule because XK is still normal to both ZK and ZK-1. So, if you want, yes. However, what we typically do is we try and make XK flow in the direction of the robot. So usually we go from left to right. And so we would normally assume that instead. Now, I mentioned as well that in other countries, of course, you've got countries in the Middle East, you know, when typically people draw the way they write. You might find that yourself where you've always done your drawings and so forth. You always wanted the flow from left to right if you speak that language, a language which writes left to right. But you might have other cultures and so forth where they go right to left. So if you do go to other countries for work, for example, you might find they actually just do it the other way, just because that's how they naturally write in their native language in that country. So do be aware that it could be the other way. In most cases, however, it will be left to right. Okay, so yeah, that's what we'll do. So basically, the x-axis is just going to be the flow of the robot wherever it's normal in the location you are. In our case, left to right. So there are sort of like sub-rules as well. The main sub-rule you will face, there's another one but it's more to do with twists and so forth, but we'll just focus on this one. 2A. And it's basically, or maybe I should call it B. So, it's if zk minus 1 and zk are parallel, then xk is chosen to point away from zk minus 1 axis. Yeah. So, in other words, if I draw this one out again, I might have zk minus 1 like this, and then in the next frame, when I move to the next frame, I find that then I got zk exactly parallel but also going up. In this case, you want your xk to move away, 100% move away. So if zk minus 1 is to the left, you definitely want to be going to the right here. So we've got to assign xk in that direction. So that's the exception to the rule. If there's already a parallel axis to the left-hand side, you must go right, or vice versa. If there's the previous axis to the right, you must go left. Again, we're going to go left to right, usually for robots. So just be aware of that. 3. So this one's a really easy one as well. Y-axis is selected to complete, well, to form the right-hand set. So again, Steve has given you some 3D printed things. You're allowed to bring them into the exam, but otherwise you've got your fingers. The way I remember is Z is always upwards, and index finger is the X. Fairly straightforward, but you always just do that pose with your hands. So for example, if I have my ZK up in this direction, and I've chosen XK to be to the right, well then my YK would be in that direction. So index finger to the right, a bit out of the camera. Alright, my background is removing it, but you can move your index finger to the left. You're going to have your thumb upwards, and you'll find that your Y is going into the screen. Very straightforward, should know that one. And then the last of the rules, rule 4, is the XK axis must intersect the previous ZK minus 1 axis. Okay, so I got another example here, so hopefully I can draw it properly. So I've got quite a weird looking robot. It's a sort of cylindrical robot, not fully cylindrical. So I got a rotary joint here. Oops. the link goes up, and then it goes into the page, like so, or into the screen, I should say. And then I got a prismatic joint, so that's often the distance, this prismatic joint, and it's got a link over here, and our end effector can be over here. We can see that if we apply our axes, purple, it's easy to see. So following rule 1, we know we must be going along the link to begin with, so we've got zk minus 1 up here. When it comes to the selection of x at the beginning, there's no rigid rule, because as you can see, well, including number 4, all the other rules are defined by what is the previous z-axis. So if we're at the start, there is no previous z-axis. So in this case, x's generally can be arbitrary, but usually you just do it in the flow of the robot. It really doesn't matter. You could have it in this direction for all I care, or you can have it in this direction. Doesn't matter. I'm just going to assign it this way, like so, and therefore completing the right hand set, yk minus 1 must be there. Correct. Yep. So now when I look at this robot over here, well, sorry, when I look at the next joint, I need to ensure that my next xk axis intersects with this zk minus 1, which, remember, the prismatic joint is further back in the page. So, to make that even more clear, I should probably just extend that into it. There we go. So, if we think about where, if we just draw out where zk minus 1 is, like so we know it's upwards in this direction. Oops, that was poorly written. And we know from the next joint that z must be flowing along the link again. So that's going to be our zk in this case. So zk is going to be along this way. So that's our plane. We must ensure that we are perpendicular. In order for our x to go and intersect, i.e. cross the previous z-axis, we need to ensure that it follows this link here. If we follow that direction, it will intersect directly with zk minus 1, and therefore that would be our xk over here. And if we draw that in, like so, that's where it would be. Then you can complete it, so y would be upwards in this case. Wait, I've got it right? No, downwards. Sorry. Yeah, downwards. I think I did that same mistake in the lecture. So yeah, if completing the right-hand set, you would find that then yk was this way. So that's what that means. You just got to generally make sure it intersects with the previous axis if you can. And those are the rules. Pretty straightforward. Now, before we can actually do the DH algorithm, there are some variables we need to be able to assign. We call these the DH parameters. So, this is what I consider the hard part of the DH algorithm. But once you do a bit of practice, so I did a worksheet, it will hopefully become more second nature. It is fairly straightforward, but for the first time, it can be a bit confusing. So the DH parameters. So I will make a little table. So we're going to make parameter. It's going to be symbol. We're going to assign them. So basically, these parameters have different properties for both Revolute, well, for the Revolute and the prismatic joint. So you're going to see how they affect each other. And when we're going through it, try and see how you, and understand why you think they can be fixed or variable. So Revolute joint and prismatic joint. I can't write very well. Prismatic joint. Okay, good. So the first variable is the joint angle. And we're going to call that theta. Now for Revolute joint, probably you can already guess, it is, if you look at here, that is our theta. Can you see my cursor? No, you can't see my cursor. This is our theta over here. So it is just basically to do with a revolute joint, is how much a revolute joint turns. Not always. It can also be, for instance, if there's a sort of bend in the link. But in the vast majority of cases, it's going to be how much the revolute joint rotates. So it's going to be variable for the revolute joint, but it's going to be fixed for a prismatic joint because obviously it can't rotate. Just put fixed. Okay, then we've got joint distance. So you've already dealt with this too. We've done. It's going to be D. We did that in lecture 3. Essentially, what D is basically it's the distance along this z-axis. So that's going to be our, oh no, not z, sorry, D in this case. Or in this case, this could also be D, just along the z-axis of the joint. So you can tell in this case that for a revolute joint, well, there's no extension to the joint, so this would be fixed. But of course, in a prismatic joint, we can extend that. We can push it along or retract it. So this would be a variable. Now, the weird two, we've got the link length. Now, this has two symbols generally. This can be given either A, and often in literature you would see it as A, or you might see it as R. Now, personally, and probably Steve does the same thing, I hope, we tend to use R, but just be aware that in literature it can be given A. The reason being is the symbol next is alpha, and alpha, well, you'll see when it comes to, it's called the link twist angle, alpha, that's the final variable, but they look very similar. So to distinguish them a bit easier when we're writing our mathematics, we typically use R. Now this will make more sense when we do it, but in both cases these are fixed. And then yeah, we've got the link twist angle. We write it as alpha. So yeah, do try and use R. It makes it so much easier, especially in the exams, for example, when we're trying to decipher what you're doing. If you've got alphas and A's and they look really similar, it can confuse us, and it just makes it so much longer to figure out if you've done the right answer or not. So please use R. It'll be very beneficial. But these extra terms are both fixed, and you'll see how they can be aligned. Okay, so let's actually see how this all works. So I'll come with a simple example first, and I'll do a bit more of a complicated example. So, example 1. Okay, so in this example, I've got, give myself plenty of space. Oops, a bit too big. I got a rotary joint at the bottom. Oops. And then up I go. I'm a bit of a perfectionist when I'm drawing, and that's a nightmare when you can't draw very well. There we go. Got something that looks like that. And that's our end effector over there. So a fairly simple robot. So what I'm going to do first is I'm just basically going to provide 2 examples of robots and just sort of show where each of those variables we've got in the DH table over here comes from. Okay, well the first thing we've got to do before we can write any variables is let's assign the axes. So first of all, quite easily we can do the z-axes. It's better to just do one at a time. So for the bottom one here, for the base frame, I'm going to assign Z0 over here. And again, I can place X anywhere, but typically I generally always just put it to the right. That's just intuitive for me. So I'm going to put X0 over here. Then your Y0, get your left hand set, and up, right, you'll find that Y should be going into the screen. Can I do that? No, it gets cropped out. So Y0 is in that direction. Okay, then we go to the next part of the robot. We can tell that the prismatic joint's flowing in this direction, so that's going to be our Z1. Now, again, X must intersect with Z, the previous Z axis, but also must be at right angle to the plane. So, if we draw this out, we can quickly go, well, Z0 is in that direction. We can see Z1 is in that direction. It must intersect Z0. Well, technically, because there's no kink in the link. That's quite a good rhyme. Because there's no, like, turn or anything like within the link. X can be technically in any direction. Whatever direction we put X, it'll always intersect. But we then have to make sure that it's actually normal to the plane of Z0 and Z1. So it could be either in this direction or that direction. Doesn't really matter. I am just going to pick this direction because I prefer things going into the plane. It's easy to draw out robots. Well, for me anyway, I find it easier if it's going into it. If it's coming out, I find it harder to visualize. But yeah, I'm going to just say X1 is in this direction. Each their own, no. There's no right answer to this one. As long as it's normal to the plane of Z0 and Z1. But I'm going to say X1 is in this direction then. Then you're going to find that your Y, let's do this right, is going to be upwards. So Y1 is going to be in that direction. Again, you need to apply it for the end effector as well. So usually for the end effector, just copy it in. So you got Y2, X2, and sorry, what am I doing? Sorry, it's Monday morning. X2 and Y2. So that's how I assign the axes. I'm just going to focus for these variables here for now on just going from frame 0 to frame 1. Okay. Oops. So let's have a look at each of them in turn. So theta. This is the angle of the revolute joint. So in this case, it's how much this rotates. So that is our theta. It's a pretty straightforward one. D, or D0 in this case, so I'm going to say D0 to begin, well, D, where D0, that is going to be the fixed distance along the direction of the rotary joint. So it's the fixed, yeah, it's the fixed distance along Z for rotary joint to align axes. So i.e. how far do I need to travel? So I did the same mistake as I did in the lecture, and this is not as intuitive as OneNote, this program, but for this case, just imagine I should have really put that into the center of the robot here. Sorry, I should have done that, but just assume, or I just quickly redraw it. I'll quickly redraw it so it's more correct. Sorry about that. I just have a weird tendency to draw those joints like that for some reason. Why? There we go. Wait. Just draw it like that to make it simple. Like that, and then yeah, put it more in the center. That's our Z. That's our X. So that's X1, so forth, and then Y1. So for D0, it's going to be how far from this axis along the joint to be aligned with the next axis over here. So that's our D0. And likewise, it's the same with D1. However, just remember that it's a variable because it's a prismatic joint. That P, the end effector, can be extended and retracted. So for D1, it's the variable distance along Z. Variable distance along Z1 to align axis to P, or Z0, sorry, Z2, sorry. So how long do we have to go along this z-axis to align with z? So that'll be our d1 over here. Pretty straightforward. So let's define the other terms. This is a bit of a simple robot, so it's not going to be the best use of it. I'll just do it below. So R. So R, what we typically call this is basically the distance along the common normal. Now there is a video in the lecture slide I have added to the Moodle page. If you go right to the bottom slide, there's a video that sort of explains this a little bit more, because if you've got twists and so forth in your robot, this will be a bit different. However, we are doing the simplified version of the DH algorithm here, whereby typically for this course we can assume that the distance along the common normal is usually just the distance along the x-axis. There's a reason why I typically set x to be in the right at the beginning, because typically that's the flow of our robot in that direction. So we're going to call this as how far along the x-axis, but in reality for more complicated robots it would be common normal. So if, for example, I'm just going to do very crudely some axes, for example, and then imagine it went into the page and then out again, and then yeah, that's right. And then we had another set of axes. The common normal in this case would be the distance from here to here. So that would be this distance here. So it can be a little bit strange. However, typically we can do this with just the x-axis, because, well, typically let me try and actually write this properly, because you'll see this in the mathematics, because it's an important term, because you'll see it in different contexts. So I have an axis like this. I need to draw it properly. If I want z that way, yeah, okay. If I have an axis like, no, I'm trying to draw it like so. Sorry, I get myself confused as well, actually. Yeah, got it. So if I have z here, x0, z0, and then to complete the set y0. So a joint, doesn't matter which one, it goes out like this, and then imagine that now there is like a 90-degree angle per se going along here. And now our new joints, I don't care which way they're going to go. I'm just going to say Z0 in this case. Sorry, Z1, sorry, that way. Let's say X1 this way, and then Y1 this way. So, just to reiterate again, R is what we call generally the common normal. So, usually it's considered the distance between here and here. What is that distance between those two axes? However, as I just mentioned before, it can be assumed generally as how long along the x0 axis do you need to go in order to align the two axes together. So, if we just, in this little example here, think about how we've done D, for example. Well, D is how far along the z-axis do you need to go to align. So if we go from here, we're going to go along the z-axis over here, and that will be our D. Now you can see in this case we're not fully aligned yet, because, well, we still have this much distance to go. And as you can see, because I pointed my x0 axis to the right, and we typically draw the flow of the robot, you can see that to finish the translation so that we can align the origins of the two frames, I just need to go along the x0 axis now. And in this case, that is what R is. Okay? So the reason I've drawn this particular example is because if we look at this one here, well, as we go up along D, along the z-axis, a distance of d0, you can see that actually we perfectly align the two axes here. So in actual fact, we don't need to move along an x to align the axis. So in this case, r is 0. There's no distance in the common normal. Going up z was enough. That's all we need to do. So that's what that describes. So that's r. So the next example, you'll see that a bit more clearly. So alpha, this one's a bit more important. So alpha, that is the rotation required. So I write this clean. This is the rotation. Well, first I should write what r is. So for r, it is the translation along the x translation along the xk minus 1 axis to fully align the origins of two frames. As you can see in this example here. When it comes to alpha, so the twist action, so you can think about where we've done the rotation, so our theta, in this case, well, it could be like a rotation like this, I don't know, just some frames in this case. But we can imagine, let's imagine anyway, that I did rotate the axis around the z. So let's imagine this first point was a rotary axis. I will go back to the previous example anyway. Well, if this rotates, then of course then this x0 would rotate, that y0 would rotate around. But in turn, the origin of the next one would also rotate. It will go all the way around like so, won't it? So if you did a 90-degree turn, for example, then this origin would rotate around like so, and then all the frames would have been rotated. So if we've got a theta equal to pi over 2, then technically our frames would look like that would be our z1 up here. x1 would still be going into the page, like so. Oops. Man, that's terribly drawn. x1 and then y1. So if you did a rotation, then that whole frame would rotate. But as you can see, we're not fully in the right direction, and we need to do another rotation in order to get it correct. So that's what the theta does. So lots of people in the lecture, when I was doing it, was a bit confused about like, well, if I apply theta, how does that affect then the next frame? That's what happens. You're modeling this sort of you're moving the whole frame, but also rotating the whole frame at once. But what basically alpha does is basically ensuring the next rotation. So what do you need to do in order to fully align the axes? So if we look in our example over here, so let's get this right. So what we need to do is we need to basically, one moment, I'm getting myself muddled up. It's actually easy to express it in alpha. I'm making new examples as I go along the spot. So, sorry, not alpha, in terms of the first example. So if we look back at our example over here, so you can see that we've translated along this, but you can see that we haven't fully rotated everything. Not everything is in the correct space. In order for us to be able to realign everything correctly in this example, we would need to rotate around the x1 axis to then align the z's. As you can see, our z0 is in this direction. Well, I've just drawn it over here, haven't I? Let's go over there. I want to get my z0 to properly transform the whole frame. I want that z0 to actually get z1. So what do? Is I rotate about the x1. Oh, I've drawn that wrong. We rotate about the x1 axis to realign. So that would be our alpha. So theta, I'll just recorrect this, is about zk minus 1 axis. And then to align the z-axes, we have to rotate about x1 to align the z. So then we've got a full transformation. So for alpha, I won't use this above example. I'm just trying to show R in this case. But for alpha, it's the rotation required about the xk axis. So it's a bit weird, but it's the current axis we're evaluating in order to align zk minus 1 to zk. Okay, so if we're looking at the above example over there, you can see that I basically need to do a rotation where I got my zk minus 1 up here. I need it to be over here. I'm going to rotate it about my current axis, my x1. And just remember, you got to do the right-hand rule. So in this case, you can see that anti-clockwise is positive. Well, in this case, that would mean alpha would need to be minus pi over 2 in order to get the correct angle. So that's what that R represents here. Okay, so hopefully you can understand where this R comes from. It's the distance along the the previous x-axis in order to align the two frame axes, and alpha is the required turn on the current x-axis to align the z's. It's fairly straightforward. So let's try and actually fully apply this to another robot. So I'm going to do example 2, and this example has all the terms more properly observed. So in this case, what I've got is I have a prismatic joint. Maybe I give myself a bit more space. I have a prismatic joint, like so. And this time I've got a bit of a kink in it. So I've got a 90-degree turn like this, where then I have a rotary joint. Not very well drawn. And then at the end, I've got another prismatic joint, like so, with my end effector over here. Okay, so the first thing I'm going to do, now we know all the variables and what they are, I am going to label all of them as much as I can. Yeah, I was hoping I think I'm just going to make this a little bit bigger, because then I can draw a bit more to it. Sorry if it's just want to make it nice and clear for you guys. There we go. Then we've got a 90-degree turn. Rotary joint. Whoops. Prismatic joint. Oops. That should be big enough. And that's P over here. So, first of all, let's draw all of our axes in. So, of course, Z0 is going to be upwards in this direction. X0 can be in any direction I want, but just for conciseness and generally I think it makes the maths a bit easier at the end, I'm going to assign X0 over here. And therefore, completing the right-hand set, you'll find that Y0 is going to be into the page. Carrying on to the prismatic, sorry, the revolute joint over here. Well, again, we're going to go along the link. So that's going to be Z1. X1 must intersect the Z0 and, no, sorry, it must intersect Z0 plane. So I'm just going to align it in this direction over here. That will hopefully align it, but obviously it's a bit strange, but in this case it will work, don't worry. Like so. Yep. And then Y1 is going to be up here. Okay. Yep, that works. Then Y2, sorry, for frame 2, well, Z2 is in this direction again. So now Z1 and X2 are both parallel, so X just needs to move away, so it can be, again, in either this way or this way. Doesn't really matter. Again, I'm just going to keep the frames exactly the same, because, again, it makes the maths simpler. And then P, I won't quite bother with P because it's just the same again. I'm just going to construct the joints for now. Okay, so let's go through this and try and sort of decipher each of the terms for the DH algorithm. So, the parameters. So, I'm going to go first from 0 to 1. So, let's look at theta 0. So, theta 0, let's do the proper definitions again. So, the proper definition of theta 0 is the rotation about the zk minus 1 axis to align xk minus 1 and xk. That is the proper definition. So I know before I mentioned, well, it's just a rotation. Technically it is. So you can see in this case, well, there's going to be a 90-degree term already, and then there's going to be a further rotation in the, for that one. So if we were to do theta in this case, if we're doing theta in this case, it's an important thing to mention here. So it's going to be theta for example 1. Well, first and foremost, we're rotating about x0. So the first thing we need to do is we need to sort of align x0 and x1. Well, you can see if we do the right-hand rule, there's going to be a rotation about the z-axis of theta like so, and there's already a pi over 2 term there. Already pi over 2. Because the x and x1 and x0 are automatically 90 degrees out. But then again, there could be a rotation being done by the revolute joint. So then there's going to be a plus theta 0 over here as well. Just bear that in mind. If there's already a fixed change in the angle, you've got to account for that. Didn't mention that in the lecture, but there you go. So, it's the rotation about zk minus 1 axis to align xk minus 1 and xk. So, again, we need to align x0 and x1. There's going to be a 90-degree turn, but then if the x-axis moves, the x0 axis moves, then this is also going to move as well. So we've got to add that theta term in as well. So if we're looking in this case over here, well, we said before in our table at the top that for theta, for a prismatic joint, it is fixed. It's not 0, but it is fixed. And as you can see, if we go back to our example here, well, our x0 and our x1 are again 90 degrees out. We need to do a rotation about the z0 axis. So like so, we need to do a rotation here to see, well, how can we align the x-axes together? And as you can see, that's our theta 0 in this case. There must be a 90-degree change, and it's always going to be 90 degrees, just because that's how the axes are aligned, and they're always going to stay that way. So we can place that there. So therefore, it is pi over 2 in this case. So you could argue, well, this is a revolute joint. Technically, if I rotate the revolute joint, that x1 is going to be also rotating as well. Well, the thing is, what we're looking at, it doesn't exactly affect the frame going from here to here, because we're looking at going from Z0, which is not affected by that revolute joint. That is fixed, right? The prismatic joint is always going to be fixed. Yeah, that revolute joint can always change, but technically, from the perspective of the prismatic joint, x1 could be any location. We just assume the revolute joint is 0 in this case. When we go from frame 1 to frame 2, then it does matter, because the rotation of the revolute joint does indeed change the next prismatic joint. But this one is not affected by the revolute joint, because it's not connected on the other side of it, if that makes sense. So we're just going to say it's plus pi over 2 for this case, to align the x-axes, assuming the revolute joint is static for our analysis for the moment. D0. Again, this is going to be the translation along Z0 to align z-axes. So in this case, you can see that we are going up from here up, 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 up. And we're going to stop there because although we haven't fully aligned it, because of course we've got to translate along the x0 still in order to do it, moving up this amount along the z-axis would align the axes until we then move along the x-axis. So that is our d0 in this case. So we haven't got a variable for it, but that's what d0 would be. And it's obviously because it's a prismatic joint, and we assume also the prismatic joint will only change in the z direction. It's not going to be prismatic, we hope anyway, in the r. You need to have another joint here, but no, it should be only in the z direction it's prismatic. So we will say that d0 is the variable. We haven't got that value. r0. So this should be easy. It's the translation along the common normal. Normal. Or in other words, the x k minus 1 axis, just for simplification, to fully align, to align the x-axes. Okay, so we go back to our diagram here. Well, you can see that, of course, we're assuming that the rotation has already occurred to align the x-axes. But to properly align them, we need to go along the x0 axis in order to fully align. So that would be our r0 over here. Again, we haven't specified a variable, so we'll just say that that's what r0 is. Oops. So alpha 0, well, that is the rotation. Give myself a bit more space. Alpha 0, that is the rotation about x1, sorry, is the current axis to align the z-axes. So if we come to this, we look at our x1 term over here. Well, you can see that z0 is upwards. You can see that z1 is along there, and our x1 is along there. You get your right hand, point it in the direction of x1, and you can see that positive is going to be in the clockwise direction. Did I do that right in the other one? I did that one wrong, didn't I? Sorry, back in this example. Just fix that quickly. Sorry guys, if you were getting confused. I haven't got you guys to correct me anymore. So that's our x, it's that way. So alpha is going to be plus pi over 2. Sorry. So back to our current example. Yeah, it's the same thing. We're going to be rotating. That's the positive direction. So again, it's going to be pi over 2 to align the two z-axes. So therefore, alpha equals pi over 2. Sorry about that. I wrote that in my notes correctly. Okay. So far, so straightforward. Again, let's just go from frame 1 to 2. I won't go to 2 to 3 because it's not interesting. So we do the whole thing again. So theta 1. So theta 1, again, it's how much of an angle do we need to align the x-axes together. So if you look at this at first, you can see that x1 and x2 are both in the same direction. Brilliant, 0. However, what if the revolute joint does rotate? So it rotates in this direction. So if it rotates 90 degrees, for example, well then x1 is going to be up here, y1 is going to be here, and z1 is going to be in the same direction, isn't it? But because frame 1 has rotated, that in turn means that frame 2 must have rotated because it's directly connected. So therefore, in order for the axis to be aligned again, well, this axis must rotate by the same amount of the same angle as the revolute joint has turned. So I also need to rotate my x2 90 degrees, so then it's upwards. So therefore, in this case, it is going to be whatever the revolute angle is. which is going to be theta 1, essentially. So if I draw that in, theta 1, what colour is the best one for this one? I'll use orange. Right hand rule, so you can see it's out of the screen is a positive angle. So whoop, that's going to be our theta 1. So depending on how much I rotate it by. So yeah, so this is dependent. On how much rotation the revolute joint has already rotated. Therefore, keep as theta 1. I know though in the lecture there was a bit of confusion about that, but just have a little think. If the rotary joint rotates, then to realign the x2 must also rotate to keep it aligned. So it's always going to be dependent on what theta 1 is. Again, for this theta 0 term, we don't care because we are always going to assume from the respect of the prismatic joint that when we're doing our kinematics that the rotary joint hasn't moved. And any rotation that the rotary joint does not affect the 0 frame at all. 0 frame is just directly connected to it, then this is just rotating about it. But because frame 2 is connected to frame 1, if one rotates, the other must rotate as well. I hope that clarifies it. Okay. D1. So D1, again, is exactly the same as the translation along Z1 to align the x-axes. Oops, missed that. X-axis. Or axes, I should probably say, yeah. So, if we go along here, you can see, what colour should I use here? Let's use yellow again. That essentially, that's yellow. D1 is going to be this length here. Nice and straightforward. R, so R1, that is distance along xk minus 1 to align the z-axes. So if we go back to this, well, you can already see in this case that as we've moved along the z-axis a distance of d, we've automatically aligned the axes together, so we don't need to move any distance in the x direction at all. So, therefore, there is no R1 in this case, so we're going to say R1 is equal to 0. Alpha 1, again, this is rotation about the x1 axis to align z-axes. So therefore, if we look back at this, well, the frames are exactly the same. No rotations required along x2 to align the axes together. So therefore, alpha 1 is also 0. And as you can imagine, the reason I'm not doing 2 to 3 is 2 to 3 is just going to be almost exactly the same as 1 to 2. Except that there is no other rotation. The rotation, because this is a prismatic joint here, the rotation that's caused by, so obviously if the rotary joint rotates, that's going to affect frame 2, but in turn that's going to be affecting frame 3 on P, but we've already accounted for that rotation going from frame 2 to frame 1 to frame 2. We don't need to do it again. It's already been accounted for. So because it's a prismatic joint, we will just say the angle 0. Okay. So that's that. So now you know how to assign all of the parameters. So this method we're learning about is an algorithm. So therefore, what is the algorithm we actually have to perform? So the algorithm. So the different steps. So first one, we got to rotate. So this is after we've assigned all the frames, of course. We need to rotate theta k about zk minus 1 to align the x-axis. We need to 2 translate along zk minus 1 a distance dk to align xk minus 1 to xk. 3 translate a distance rk along common normal. Oops. Along common normal, technically, or the x-axis, xk minus 1 axis, to align z-axes. Or in other words, you can also say to bring the origins of xk together. I wrote that another way you can sort of express what's going on, but technically it's to align z-axes. That's the technical term. And then 4, you need to rotate alpha k about the current x-axis. Oops. To align zk minus 1 and zk. And that's the algorithm. So we've got an algorithm, but now we need to, well, to perform the mathematics in order to actually do it. So just remember, the DH algorithm is still trying to achieve the same thing as what we did with the homogeneous transformation matrix. It's to be able to understand where the end effector is in reference to the base frame. But we're just trying to make it in a bit more of a coherent method for which then every engineer can follow. Sorry. So, of course, there's going to be some mathematics involved. But by applying each of these terms, we can make one coherent matrix in order to apply the algorithm on. So, by following the algorithm, in this order, I should say, in this order, we can generate matrices, matrices for a unified DH transformation matrix. Okay, so if we do 1, so start with step 1, well, as we just said, it's a rotation of theta k about the zk minus 1 axis. So we're doing a rotation about z. So go back to lecture 3 on homogeneous transformation matrices. So rotation about z axis, or theta. Well, Rz in terms of theta is just the standard matrix we did before. So it's going to be C theta. So just remember when I'm writing this, C theta means cos theta and S theta is sine theta. You're going to understand why later on. It becomes not the nicest looking equation if you had to put cos and sine everywhere. So we're just doing it shorthand. So then we're going to go minus S theta 0 0 S theta C theta 0, 0. Now we're not talking about a translation along Z, so we're going to keep that constant there. And then of course the bottom row is always going to be 0, 0, 0, 1, just to make the mathematics work. But there we go. That's one matrix for the first operation of DH. 2, we're going to do a translation of D along the Z-axis. So, I'll just call it D along the Z-axis, otherwise it might cause confusion. There we go. So again, you should know what this equation is already. That's just basically a translation of Z of a variable D, and that's equal to, so it's basically going to be 1s all the way down with a D in the Z for the translation, and lots of zeros. That's the next translation matrix. 3. This is going to be the translation along the common normal, but as I keep saying, it's a translation along the previous Z-axis, so it's a translation along the X-axis of R. So again, we're going to say there's a translation of X of a variable R. So I guess you can gather what that's going to be. That should be 1, 0, 0 R followed by lots of 1s. I'm not going to say 0 over and over and over again. There you go. That's the next one. And then number 4. That's going to be the rotation alpha along the Z, about, I should say, not along, about the X-axis. So again, should be fairly straightforward. So there's a rotation of X of a variable alpha. So it's just going to be the rotation about X, homogeneous transformation matrix. So X is assumed constant. And then we just fill out what we already know. Oh, sorry, not theta, alpha. Sorry about that. Alpha minus S alpha, S alpha, C alpha, then 0, 0. And that's that. Pretty straightforward. So now what we've got to do is just put them all together. So to get a unified DH matrix, which we're going to call AK, we just have to combine all the operations. So, in other words, we're going to say that AK is equal to the rotation about Z of theta, multiplied then by a translation about Z of D, multiplied by a translation of X in terms of R, multiplied by a rotation of X in terms of alpha. And then when you combine them all together, which is not the nicest equation, you can get one big matrix. I believe you are provided this in the exams. You don't need to remember it, but probably beneficial you do. That AK is equal to, now let's see if I can fit this on the page. So it becomes C theta K minus S theta K C alpha K S theta K S alpha K dot dot it's going to be RK cos theta k. Then you got S theta k, C theta k, C alpha k, minus C theta k, or S alpha k, RK S theta k. Then there's 0. S alpha k, C alpha k, dk, and then on the bottom 0, 0, 0, 1. And that's the DH matrix. So, as I mentioned before, there is an additional rule. When we came to do the DH rules above, well, sorry, all this, I said 2, 2b, and so forth. There is a slight different rule when it comes to when you got like twists and turns. We're not going to do that in this course as too much. You have to be aware that they exist. So there's a video. If you look at the main lecture slides I've done, well, Steve technically did them. Right at the bottom, there's a video on YouTube. Please do have a look to make sure you're aware of that rule, because although we're not doing it, it's a very common rule, and it's basically when there's a shift on the x-axis and then you're actually drawing a common normal R. Have a look at the video, you'll see what I mean. But yeah, so I've done an example in the other notes. I'm going to halt it there. And that's how you get the matrix. Please have a go at the worksheet. I'm going to produce, right after this, I'm going to produce an answer sheet for the worksheet. But do make sure you try and go through them yourself, and then you can see where you're going wrong if you are going wrong. Alright, cheers.